Right, so we proved this. We're almost done now. We're going to apply Cauchy-Schwarz. Cauchy-Schwarz says that summation over I of ai bi is at most the square root of the summation over I of ai squared times the summation over I of bi squared. So here we are summing over edges. These are the AIs and these are the BIs. So we get here. Let's see how much progress we are making. This is already essentially the numerator of the Rayleigh quotient of y. This is something that we need to understand a little better. So here it's possible to apply Cauchy-Schwarz again, or actually a much simpler fact, the fact that a plus b, when a and b are non-negative, squared is smaller than 2a squared plus 2b squared. That's because if you look at this expression minus this expression, that's just this. And it's greater than or equal to 0. So from this observation, we can say that the summation over the edges of yu plus yv all squared is going to be at most the summation over the edges of 2yu squared plus 2yv squared. Factor out the two, what you're going to get is summation over the edges of the square of the endpoints. So then for every vertex, the corresponding yv square will appear d times, where d is the degree. So that's why we get this much simpler expression here as an upper bound. Now we are really almost done. Let's look at what is the expectation of the number of cut edges divided by d times the expectation of the small side of the cut. We computed that the denominator is actually identical to this number, and we proved that the numerator is at most this number. So simplify a bit, and this is what you get. This is twice the Rayleigh quotient of y. And when we constructed y, we made it so that its Rayleigh quotient was at most the Rayleigh quotient of x. Now there is still one more observation. So it would be tempting to say, all right, the average of the number of cut edges divided by the average of the small side of the cut is at most this much. So the average of the expansion is going to be at most this much. But if you have two random variables x and y, you cannot say that if the expectation of x divided by the expectation of y is at most some upper bound, then also the expectation of x over y is going to be at most this much. In fact, you can find counterexamples. So you need to argue a little more carefully, but it is possible from something like this to argue that x over y must be smaller than the upper bound, at least with some probability, strictly bigger than 0. So let's see why. We can multiply both sides by d times the expectation of this set and bring this to the other side. Apply the linearity of expectation. And now we have that the expectation of this expression is at most 0. For this to be true, at least sometimes this expression must be smaller than or equal to 0. Because if it were always strictly positive, its expectation couldn't possibly be smaller than or equal to 0. So what's the sample space of this random variable st? It's the ways in which we choose t. So there must be some choice of t such that this expression is smaller than or equal to 0. And when this happens, this quantity is at most the square root of 2rx. What is this quantity? It's the expansion of the set st. So what did we prove? That with positive probability, if we pick a threshold t according to that distribution, and then we look at the corresponding sets that are defined by that threshold, the sets that we pick are such that the smaller set has expansion at most the square root of 2 over x. So if a random threshold t has this property with positive probability, it means that some t exists. And now you're done, because the sweep algorithm only needs the existence of this threshold, and then it just finds it. And now we have proved what we called the main lemma, that for every graph, once we have a vector whose entries sum to 0, there must exist some threshold for which the expansion of the sets that we get by picking the vertices labeled less than a threshold and the set labeled by the vector as bigger than the threshold is a partition of the vertices into two sets, both having expansion at most the square root of twice the Rayleigh quotient of the vector. And once we plug into this general result an x which is an eigenvector of lambda 2, this Rayleigh quotient will be lambda 2. So here we get the expansion of both sets, so in particular of the smaller of the two, will be at most the square root of 2 times lambda 2. And these sets will be among the sets considered by the sweep algorithm. Because if you sort the vertices according to the value of x, this will be an initial segment of the sorted order, this will be the remaining segment of the sorted order. So those cuts are precisely the cuts considered by the sweep algorithm.